to get these numbers. I'm going to give you a couple of more examples, okay, from the comparison test to make sure you have no difficulty. Then I give you those a new one. Okay, so the example is we want to determine, okay, determine whether the given series, the series, okay, converges or diverges. Okay, this is it. For example, this is going to be the first one. The first one is a sigma of 1 over radical n. Okay, radical n minus 1/2. Okay, when goes from 1 to infinity. So the way you do it, you just think about it. What is going to be the closest series to this one? So if you shrink the denominator, means when n goes to infinity, if you forget about the 1/2, you see, if you forget about the 1/2, it's 1 over radical n, which is 1 over n to the 1/2. It's a p series. P is 1/2 is less than 1. This must be divergent. The way you are going to do the comparison, as I told you the other night, is just shrinking. You should shrink this one. So you can say that this series is like, it's a radical n minus 1/2. So this is going to be like, almost like 1 over radical n. Okay, and you know that 1 over radical n is going to be divergent series. So what we can do is, so this is going to be equal to sigma of 1 over n to the half. You see, and you know that this is going to be what? This is a divergent p series. Okay, this is a divergent p series. So what you're going to do, you have to use the limit comparison test to compare it. You see that the limit of an, okay, divided by bn and goes to infinity, which is the same as the limit of an is this one, okay, 1 over radical n minus 1/2, and the bn is this one, 1 over radical bn when it goes to infinity. You have to prove that this limit is not 0. So that would be the limit of the first part is 1 over radical n minus 1/2. Use the reciprocal did give you radical n over 1. Okay, so this is going to be simply equal to the limit of radical n on the top, and this is going to be radical n minus 1/2 down the bottom when it goes to infinity. It's like if you call the top one t is a t over t, the limit would be 1. Or you can shrink it. The leading term on the top is a radical n, and this is the radical n. N goes to infinity, this limit is 1. 1 is not equal to the 0. So according to limit comparison test, you see this is the an and the bn. Sigma of bn is sigma of 1 over n squared, n to the 1/2 is divergent. So by the limit comparison test, your series is also divergent, okay? So consider the same limit of 1 over n radical n, which is the same as the sigma of 1 over n to the 1/2 diverges, and by limit comparison test, LCT, the given series sigma of 1 over radical n minus 1/2, okay, diverges. And then you're done. So this is quickest way. You can do it on also with the comparison test, but this one is much easier. Okay, so quickly you should be able to find out the connection yourself. Okay, to get it right away. Maybe another one to get to know this method, very easy method. Because this is over 2n squared plus n plus 7, n from 1 to infinity. See, again, you want to compare it. So shrink this one. see, you can shrink the inside one or just, the outside. It would be the same thing. You can say that this series 1/2n² plus n plus 7. When it goes to infinity, you can shrink the denominator to its leading term. It's like this one. And you know that it's a convergent series. In future, if you say convergent, we accept it. This is a convergent P series. You know that because n is 2. So use the limit comparison test, limit of an over the Pn, n goes to infinity. So it's going to be limit of n goes to infinity. Your an is the given one, 2n² plus n plus 7. And this is going to be 1/2n². So it's going to be limit of the first one multiplied by the reciprocal of the other one. You see, reciprocal of the other one. So again, on the top, you get the limit of the 2n² on the top. And that's going to be 2n² plus n plus 7 on the bottom. When it goes to infinity, the leading term on the top would be 2n². Down the bottom would be 2n². N goes to infinity, they cancel out to get a 1, which is not equal to the 0, again, by limit comparison test. Since the shrinking one is convergent, so the original one would be convergent to n. Okay, very nice method. So you claim that the sigma of 1/2n² converges, and you have to explain it on the test by limit comparison test, the given series, sigma of 1 over, because both of them would be behaving like each other. So this one also is converges or convergent, and you're done. It's a very, very nice, nice method to be able to take care of it. Okay, there is only one that you better use with the comparison rather than limit comparison test. This is the one. We're going to change it in future, but it's going to be limit of the sine square of n over n² plus 1. Because of the sine, you just compare it with the leading term or with the series. You see, sine square is always less than 1. So this series, you see, is going to be compared with, you see, you claim that the sine or the sine square of n is less than or equal to 1. So the sine square of n over n² plus 1 is less than or equal to the 1 over n² plus 1. See? And this is going to be less than 1 over n². Because you get two fractions, one the highest denominator is going to be smaller, or the largest denominator. So basically the sine square of n over n² plus 1 is less than 1 over n². But sigma of 1 over n², you know there's a P series convergent. Is a convergent, okay, convergent P series. And this time by comparison test. By comparison test, okay, by comparison test, the given series is convergent. So the sigma of sine square of n over n² plus 1 is convergent. So, you know, you should be ready for it to get the limit comparison test or just going with the comparison test. Okay, it's very, very easy test to apply and very, very popular. So anytime you can shrink your test, okay, you can shrink your terms to get to the P series or geometric series you better use this method to get through it. Now, there are two more tests in your book. They talk about it later, but we're going to talk about it now because that would be useful for us. So one of them is called the ratio test. What is the ratio test? Remember, for the time being, we're just dealing with the series with the positive term. So we are going to take care of that when the terms are not going to be positive. It's going to be a very easy test, and this is the only one. Then we are going to use it after your quiz, if you like, especially to the end part of the course, which is going to be the power series. Use this one. That's why I want to introduce this one early so that gets used to it. This is it. See, if you have a series, suppose, again, suppose that sigma an is going to be a series of positive terms. This term are all positive. Is a series with a positive term. Positive. All these tests are going to be applying only to the series with the positive terms. Positive terms such that, you see, such that this limit exists. A limit of an plus 1. You see the n plus 1 term over the an when n goes to infinity. This limit exists and we are going to call it L. Okay, so you get the ratio of two consecutive term of your series, and then you find it happen to be L. Now, if this L is going to be less, it's like geometric series. If L is less than 1, then your series is convergent. Very easy. Then sigma of an, okay, converges. That's case 1. Case 2, if L is greater than 1, then your series is divergent, or this series diverges. Okay, very easy to check. An plus 1 over an. When it goes to infinity, that would be divergent. If L is equal to 1, you are unlucky. You see, it's going to be equal to 1. You cannot use the test. So this means this is the wrong test. You have to go. You may have a convergent series or divergent series. You don't know. So if this is going to be the test, bad luck. Okay, the test fails. This means go and test another. You cannot say that on the test that, you know, we ask you to check whether the set is going to be convergent or divergent. You cannot say that the test fails. Okay, your test fails. So you have to go back and check another test. Okay, very useful one. You will see for the rest of the course we are going to use it. Now the question is how we're going to use this one. You say use this one if your series is going to be especially contain some factorial terms, or going to be a kind of rational function, especially if you see any factorial. You know that 2 factorial, 3 factorial, or n factorial is going to be the sum of, let's just remind you as a remark, you see n factorial is going to be the product of all numbers up to the n. Is a 1 times 2 times 3 times n minus 1 times n. That's n factorial. Okay, so for example, if you have a 3 factorials, it's going to be 1 times 2 times 3, which is 6. So we already got this idea from calculus 1. Okay, so if you see this type of kind of factorial terms, that's the best test to use it. Okay, so let's give example, ratio test. Ratio, very popular. The main series that we're going to consider for the final part is going to be power series. And this is the only test that is going to be used. Okay, so let's check. You can't miss it, the type of the series. You can use it anytime you like, of course. but we usually use it for this type of series. So we want to determine, again, determine whether the series converges or diverges. Series converges or diverges. Okay, and there you are, the typical one that you have to use this method, sigma of 1 over n factorial. And you see this type of series, you must use the ratio test. You have no other choice. You see, you have a look. Is it geometric? No. Is it p-series? No. Can you shrink it into the p-series so that you use a limit comparison test? No. So you go for the ratio test. Okay, for ratio test, you have to form this quotient solution. So we have to go for the limit of, you see the top would be an plus 1, the bottom one would be an goes to infinity. So it's going to be equal to the limit of, on the top an plus 1, you change n into the n plus 1. So that you 1 over n plus 1, okay, factorial. An would be just 1 over n factorial, and goes to infinity. Now the ratio of two fractions, you write the first one multiplied by the reciprocal of the other. So the limit of 1 over n plus 1 factorial times that by n factorial over 1. N goes to infinity. So it's going to be equal to the limit of, now the top you have n factorial, the bottom you have n plus 1 factorial. Now you have to simplify it. You see n factorial is everything up to the n. You see this is going to be limit of, on the top you get 1 times 2 times 3 up to the n. But this is n plus 1 factorial. So we get up to the n, then n plus 1. Or simply, this is going to be what? N factorial times n plus 1. Now these are all would cancel out. So you end up with the limit of, on the top you get 1, on the bottom you get n plus 1. N goes to infinity. You know that the degree of the bottom is higher, so this is a pizza problem, and that would be 0. Okay, so the limit of an over bn, n goes to infinity, is equal to the 0, and 0 is less than 1. So as you can see, the limit comparison test, if L is less than 1, the series converges. Bigger than 1, diverges. So in this case, okay, so in this case, you can say that by the ratio test, that the series converges, okay, sigma of 1 over n factorial, n from 1 to infinity converges. It's a very, very nice test. And this is, in fact, as I told you, this is the only test that you can use for this type of problems. Okay. So that's first one. Give you another one. The other one is this number 2. The series in question is again very popular series, n over 2 to the n. Okay, and from 1 to infinity, you want to check this one. Again, you say this is not geometric, because for the geometric you need a 1 on the top, not n. Of course, it's not a p-series. Okay, so what you have to do is you have to use the ratio test to see if you can check this one. Okay, the ratio test. So we're going to form solution. So it's going to be the limit of an plus 1 over an, n goes to infinity. So we're going to check this one. It's going to be equal to the limit of n goes to infinity. So a n plus 1, you change all the n into the n plus 1. So that give n plus 1. That would be 2 to the n plus 1. And this would be repeated n over 2 to the n. You have to simplify it. So you write the first fraction, limit of n goes to infinity. The first one is n plus 1 over 2 to the n plus 1, and use the reciprocal that give you 2 to the n over n. Now 2 to the n and 2 to the n plus 1 would 2 to the n would cancel out. So the left over here is going to be 2. So this is going to be the limit of the top. You get the 1 that give 1 times n plus 1, n plus 1, and you get 2 times n, which is the 2n. N goes to infinity. You know that this limit would be 1/2, because you shrink the top into the n, and this one to the 2n, n goes to infinity, that give you 1/2. And 1/2 is less than 1. See, limit of a n plus 1 over a n when it goes to infinity is less than 1. So by the ratio test, your series sigma of n over 2 to the n, is convergent. See, these are very typical problems that you have to use the ratio test to take care of it. Okay. So let's have another one to see how we're going to get it when it's going to be divergent. This next one is also very popular series, and this is the only method that we can apply to get it. Okay, let's see what's special about this one. One of those series that you have to know how to handle it. It's going to be n to the n, and this is going to be n factorial. Again, you see it's very unusual one. It's not a P series. It's not a geometric series. So what is the choice? The choice is going to be ratio test. Okay, because of the factorial that you see over here, use the ratio test because these factorials can be canceled out or can be simplified by the ratio test. Okay, so this is going to be the solution. So let's do the ratio. It's going to be the limit of, we have the an over the bn, n goes to infinity. So it's going to be the limit of an, you just repeat it, n to the, oh, I'm sorry, I made a mistake. I just want to use the, what's that? Limit comparison test. This is an plus 1, an. Okay, so we have to change this into the n plus 1 to the n plus 1. And this is going to be n plus 1 factorial. This is going to be n to the n, and this is going to be n factorial. Okay, when n goes to infinity. Now write the first one, multiply by the reciprocal, it's going to be limit of, the first part would be n plus 1 to the n plus 1. And this is going to be n plus 1 factorial, times it by, you switch it, n factorial, n to the n goes to infinity. Now you have to find this limit, you have to simplify it. You see, n plus 1 factorial is like 1, 2, 3 up to the n times n plus 1. So it's like n factorial times n plus 1. So that will enable you to simplify this. So you see n factorial, that would be out. So that give you 1, that give you n plus 1. Okay. So 1 n plus 1 and the 1 n plus 1 would be simplified. This n plus 1 is n plus 1 to the n. So this would be simplified. So what's going to be the final answer? It's going to be limit of, on the top, you get n plus 1. Okay, everything to the n, because one of them is cancel out. And down the bottom, we get n to the n when n goes to infinity. Okay, so I simplified n factorial, so that give me 1. And over here, I have n plus 1 and n plus 1 on the top to the n plus 1. So I drop one of them, so the new power would be n. Okay, and this limit is very popular one that I find that for you before as a sequence, and I told you that we're going to use it. You see, if you break it into this form, you see, and when n goes to infinity, and if you break the inside one, n divided by n, that give you 1 plus 1 over n to the n goes to infinity. I did this limit for you before, and I told you that this is going to be equal to the e. You have to make a note for yourself. You can use this one anytime you like in this course, that this limit is equal to e. Okay, so what we did, we proved that the limit of an plus 1 over an when n goes to infinity is equal to the e. Remember, e is 2.7, so e bigger than 1. Since it's bigger than 1, by ratio test, the series diverges. So by the ratio test, okay, ratio test, the given series sigma of n to the n over n factorial, when n goes from 1 to infinity, is convergent. Sorry, is divergent. Divergent because that ratio is greater than 1. If the ratio is less than 1, in that case, okay, your series is going to be convergent. Okay, so this is how you use the ratio test. Okay, now I'll give you an example to see if you get the wrong choice, then you'll be in trouble. Okay, so the number 4 is, you see that L, that ratio must be less than 1 for convergent, greater than 1 for the divergent. But sometimes you may use, you use the wrong test. So that would be number 4. In number 4, this is what we have. You see, look at this one. Sigma of 1 over 2n minus 1. You see, in this one, you don't need the ratio test. Because if you shrink it, it's like what? It's 1 over 2n. It's like 1 over n. Remember, harmonic series? It's a divergent series because it's a divergent p series. So we can use limit comparison test and be done. Suppose you made a, you made a mistake and you tried to use the ratio test. You see what you have to pay for it. You see the solution. So, we have a look at it, you say, oh, it's a p series and we're done. But suppose you missed it. If you missed and you try to use this test, okay, n plus 1 over an goes to infinity. So you have to change the n into the n plus 1. So the top would be 1. That would be 2 times n plus 1 minus 1. And the bottom one would be 1 over 2n. N goes to infinity. Okay, so you write the first fraction, multiply by the reciprocal of the other one. It's going to be 1. And I'm going to multiply this 2n into 2 inside. That gives me 2n plus 2 minus 1. And I use the reciprocal here. That gives me 2n over 1. So this would be the limit of, on the top we get the 2n, down the bottom 2 minus 1 would be positive 1. So that gives you 2n plus 1. You see when it goes to infinity, the degrees are the same. 2 would be 1 because if you shrink it in the leading term, 2n, n goes to infinity, that gives you 1, which is very bad. Because what you have here is the limit of an plus 1 over an. N goes to infinity, you get 1. We cannot use the ratio test when it's 1. We can only use it when it's less than 1 or greater than 1. So this means the ratio test fails. See the test. the ratio test fails, and you cannot use it. So you have to start it over. You have to think about it. What I'm going to do about it. So that was the wrong test. So let's start it over again. So you start it over and you realize that, oh, this is very much, if I shrink it, it's like 1/2n. Okay, which is P series, is a divergent P series. So this means use the limit comparison test for your test. You see the limit comparison test, remember, limit the AN over BN and goes to infinity. We compare it with a known series. So we check this limit, it's going to be limit of 1/2n minus 1, and that would be 1/2n, and goes to infinity, which is the same as writing the first one multiplying by the reciprocal of the bottom one. So that gives you the limit of 2n on the top, 2n minus 1 on the bottom, and goes to infinity. That gives you 1. But 1 is not equal to the 0. Remember, in the case of the limit comparison test, you must get a non-zero number, non-zero positive number. So by limit comparison test, the series, okay, your series or the series sigma of 1/2n minus 1 is divergent. So you got to be careful. Sometimes you may use the wrong test. If you use the wrong test, you go back and correct it. So the ratio test can be used only when L is less than 1 for the convergence series and greater than 1 for the divergent. Okay, but it's a nice test. And as I told you, after, when we get to the power series, which is the main part of the course, this is the only test we are going to use. So it would be useful for us, but for the time being, with the numerical series, this is most we can do. Okay, now there is another test that whatever you can do with the ratio test, you can do with that test too. That would be useful for some very specific one. Okay, so this is going to be the one we call it root test. Okay, so what's going to be the root test? The root test is the last test that we have for the series with the positive terms. What is the root test? Okay, there you are. Suppose you have a series again, suppose sigma n, the term must be positive again, is a series. Okay, it's a series with positive term. With positive terms. These ANs are positive. Okay, such that you see this limit exists, limit of the n root of the AN. AN is your general term of the series. You take the n root, n goes to infinity. You find this limit, and suppose this is L. Then whatever you did with the ratio test is also true for this one. So the conclusion is going to be, if again L is less than 1, the series sigma n converges like geometric series. And if L is greater than 1, again like geometric, the series diverges. Okay, the series sigma n diverges. Okay, and if it's equal to 1, you are unlucky. You cannot use this test. Okay, it's like the ratio test, the test fails. The test fails. So that's going to be the ratio test. Now the question is when you are going to use it. You see, when you use it, when this an is containing the term, like, you know, you have the lots of powers, n to the n, n to the 2n, 3n. So it's very typical one, really. You can't miss it. And these are going to be the popular examples that you can have. Very limited choices, but useful test. Okay, so what's going to be the example? We want to determine okay, determine whether whether the series again converges or diverges, converges or diverges. This is going to be the one. And now you see the way we are going to realize this must be used. You must use the ratio test. Is this root test? Look at this one. 4n minus 5 divided by, you have a couple of them in your book, 3n plus 1, everything to the n. You see, as soon as you see parentheses raised to the n, the best test is the root test, because when you take the n root, this n will disappear, and the leftover is very easy to, okay, to check. Okay, so you can't miss it because of this power of n here. Okay, because this is your test. Your test, you take the n root of the an. As soon as you take the n root, this n will disappear, and the leftover easy to, to find the limit of the leftover. So a solution is going to be, there you are, the limit of the n root of the an. Your general term is going to be the limit of n goes to infinity. There you are. You see n root of 4n minus 5 to the 3n plus 1, everything to the n again. So this n and n would cancel out. So you arrive at the limit of 4n minus 5, 3n plus 1, n goes to infinity. There you are. In rational sequence, the powers are the same. Or just you shrink the top. It's going to be limit of the leading term 4n, 3n, n goes to infinity. That give you 4/3. 4/3 is bigger than 1. By the n root or the root test, the series diverges. That's it. So you have to mention that which tests are going to use. By the root test. By the root test, the series sigma of original one. 4n minus 5, 3n plus 1, everything to the n is divergent. Sorry, is convergent. Oh no, divergent, bigger than 1. Divergent. Okay, divergent, and you done. So very easy test. Just use it when you see the original term. It's going to be raising to the n, raising to the 2n. So you can't miss it even on the test. It's going to be easy question. Okay, give another one because that was divergent, something which is going to be convergent. Number 2. Number 2 is going to be sigma of 1 over ln of n plus 1, everything to the n, you see, n from 1 to infinity. Again, you see, because of the power n here, the best test is the root test. Because you take the n root, this n will disappear, and the leftover is easy to, to work with. So, solution, that would be the limit of the n root of an. N goes to infinity. So that would be the limit of n goes to infinity. It's n root of 1 over ln of n plus 1. Okay, everything to the n. So n and n disappear. So that give a limit of n goes to infinity, 1 over ln of n plus 1. When it goes to infinity, the denominator would be infinity. Ln of infinity is infinity, so this would be like a pizza problem. It's going to be 0. Okay, so you get the limit of the n root of the an, n goes to infinity is 0, and the 0, of course, is less than 1. So by the root test, your series, okay, series, sigma of 1 over ln of n plus 1, everything to the n, converges. And you're done. Okay, so it's useful test, but you better avoid to use it unless you know this is going to be of this type, really. Don't use it for the other ones because it would make things complicated. That's going to be useful for this group. And this is where we're going to use it. And that's it. Now we talk about all the, okay, this is it. You see, this is the one we already talked about it. If the limit of the general term not 0, the series divergent. A geometric series, if the absolute value of the common ratio less than 1 converges. Telescoping series depends on the leftover of the Pn. A P series, clear, if P is bigger than 1 converges, less than 1 diverges. We haven't talked about this one. This is section 11.5, alternating series. We talk about it later. That's the integral test. Integral test instruction will be given to you because this is one of those tests that you don't like to use unless you've been told. So we're going to give you use integral test to do it. Remember, that's the general term of the series. We look at the improper integral. If the improper integral converges, then the series converges. This is the one that the root test that I did. They put the absolute value around it because they want to use it in general. But for the time being, we use it for the series with the positive term. So over n are positive, we don't need the absolute value for the time being. Okay, the limit less than 1 converges, bigger than 1 diverges. This is a ratio test. Again, I use it for the positive series, so I don't need the absolute value. We talk about the absolute value later on. Okay, so that gives us the convergent. And that's a direct comparison test. Remember, an less than bn. If bn converges, this is convergent. The even diverges, the sigma bn would be divergent. But the best thing to do is the limit comparison test. Limit of the a and bn, if this is a non-zero element, non-zero number,